ਵੀਰੇ ਹੁਣ ਵੀ ਲਾਈਵ ਨਾ ਹਰਵੀਰ
National Science Day is spreading the message of the importance of science in daily life of the people. The theme for 2018 Science Day is Science and Technology for a Sustainable Future. गहन आवश्यकता है इस विषय में चिंतन मनन और पूरे मनोयोग से कार्य करने की कि भविष्य में उत्तरजीविता बनाए रखने में विज्ञान एवं प्रौद्योगिकी का सक्षम उपयोग। इस अवसर पर भारत सरकार की ओर से देश भर में प्रबुद्ध वैज्ञानिक चेतना और मजबूत वैज्ञानिक आधार के विकास के लिए विशेष कार्यक्रम आयोजित किए जाते हैं। साइंस एग्जीबिशन, क्विज, डिबेट्स, संगठन में भी इसी दिशा में आयोजन हुए। साथ ही जन सामान्य और स्कूल के विद्यार्थियों के लिए संगठन में आज ओपन डे मनाया गया। सर्वप्रथम मुख्य अतिथि के औपचारिक स्वागत के लिए हम महक से अनुरोध करेंगे निदेशक महोदय को पुष्पगुच्छ दें, जिससे वे मुख्य अतिथि को फूलों से स्वागत करें। Now we request our director, Professor Aarti Sinha, to formally welcome everyone and briefly tell about the event, today's event, and also to introduce us.
Good afternoon to you all. First of all, I welcome our own professor, Professor A.K. Ghatkar, for coming to our organization and accepting our invitations for delivering 2018 National Science Day lecture at CSIO, Chandigarh. In spite of his family and other commitments, sometimes this event was about to be postponed, but it is because of his enthusiasm and his commitment, interest to mix and excite the students' population particularly. He preferred to come here, and so we are all very grateful to you for coming to our organization. Your lecture in terms of the each sentence inspires not only to us, generation of their students. So your presence is a very valuable to all of us. On the audience side, we have our own scientists, students, and also I feel very satisfied to look our superannuated scientists who have come here, and some of the other scientists from the other institutions. I welcome them also to be here, and I welcome you all to be present in our institute's important function, that is the National Science Day 2018, to you all. I was asked to explain a bit briefly about today's function. So today's function, as it was told, it is the National Science Day. We are celebrating based on the discovery of the Raman effect, which is very important tool for an institution like us. The basics and details will be taught by today's lecture by Professor Ghatkar. But I must say, when a light is incident on any molecule, then the transferred light outside which you see, there is this light, but you get an additional other wavelengths of the light that gives the signature of the molecule from where the light is passing. So this is a very important tool for us, particularly in institutions like us. We use a many sensors and Raman spectrometer. This gives us a very good tool for designing different type of an instrumentation. So for these institutions, each and every one, including the administrative staff, I expect that they should know what is our effect. And nobody can make them understand better than you, sir. So this is a very important issue. So this is the National Science Day is celebrated based on the original work done by Sir C.V. Raman when India was under the Britishers, and he was working in a, you can say, an almost isolated place with a less of opportunity, and still he could do this kind of a research work. And this gives us a task to all of us scientists that we should also think in terms of the original contribution in the science. If he can do in a bad atmosphere, today's India is a much more developed country and we have all facility. So we have a responsibility to do a similar or even better outstanding research work. So National Science Day, in honor of this effect and his recognition worldwide, Government of India in the year 1986, through the National Council for Science and Technology Communication under the DST, had given a proposal to the Government of India that this is a very important contribution of an Indian scientist which has affected the worldwide and many technologies. So this should be recognized as a National Science Day. And from the year 1987, government has desired that we should celebrate February 28 as a National Science Day. And since then, almost all institutions, they celebrate National Science Day to propagate the studies of the science, its effect to the normal human life, their daily life, how it is impacted. So since then it is started, but around 1999, every year the Government of India decides a theme of the National Science Day. This year, as it was explained by our Hindi officer, this year's theme is a science and technology for sustainable future. A sustainable future. Last year's the theme was their science and technology for especially able people. And as a result, last year also we celebrated National Science Day. We have organized an exhibition of the technology which we have worked through the biomedical instrumentations, and it was widely seen by many corners of the people, of the society. So National Science Day in that sense is important functions for any of the scientific institutions. So this is the brief introduction of the Science Day, and we do celebrate it as one of our national festivals. Now, coming across to a brief of the institution. Indeed, our instrumentation, our institute's name is a Central Scientific Instruments Organization. But any of the instrument works are designed with the basic sciences. So we have all varieties of the department, applied and basic research also. And in the last 2.5 years, I must say that we have progressed phenomenally to the general audience. And here, I also say that I'm very happy to announce that almost 25 technologies from this lab have been transferred to industry. And continuing this technology transfer has not weakened our interest in doing a basic research. Publications in a good science that is in this science, which is normally does not come from the engineering lab, has also appeared in the last year, particularly for Ismail and Faber classification from our scientists. And almost scientists have maintained one research paper per scientist per year. This we have improved from there, and we have also enhanced the basic facilities. So I must thank and congratulate the scientists who have contributed and shown their visibility in their scientific work at the national level as well as in international level. And based on this work, they have been suitably rewarded also. CSIRO last year was given a National Innovation Merit Award by NRDC for completing the installation of earthquake warning systems. This is one of the important and need-based technology, and it was recognized by our peers. So our scientists are actively pursuing their scientific pursuit as well as designing and developing the instruments for the mandate for which the CSIRO is created. Now, next, I have a privilege and pleasure to introduce my own teacher in this formal function. So, Professor Ajay K. Ghatak has been an eminent professor of physics of our time and extremely popular teacher among generations of his students. He obtained his MSc degree from Delhi University and PhD from Cornell University, USA. His areas of research are fiber optics and quantum mechanics. He has several books in these areas, and they are widely used by these students, teachers, and research professionals worldwide, which include Introduction to Fiber Optics, Optical Electronics, Quantum Mechanics. The first edition of his undergraduate textbook on optics has been translated into Chinese and Persian. Is one of the latest books. Is on the spatial theory of relativity, and its many other versions have also been published. Some of other books authored by him are Lagrangian Optics, Monogram of Airy Function, Inhomogeneous Optical Waveguides, Lattice Dynamics, Lasers, Fundamentals and Application. One of the most recent books published from SPI is Polarization of Light with Application in Optical Fiber, and some other recent books which we have come to know are given here. Some of them are Light and its Many Wonders, Experiments with Light, Fiber Optics through Experiment, Problems and Solution, Electromagnetics, and variety of the book. The other one is the Albert Einstein, The Story of a Genius. These are some of his recent books. In 1995, he was elected Fellow of Optical Society of America for distinguished service to optics education and for his contribution to the understanding of propagation characteristics of gradient index media, fibers, and integrated optical devices. He is also Fellow of SPI, the International Society of Optical Engineering. Professor Ghatak is indeed Fellow of several national academies and institutions like National Science Academy, IET, Optical Society of India. He is a recipient of prestigious SS Nagar Award in the year 1979, instituted by CSIR, Government of India, Meghnad Saha Award for outstanding research contribution in theoretical science in 1991, and 1998 Galileo Galilei Award from International Commission on Optics, and 2003 Khwarizmi International Award from Iranian Research Organization of Science and Technology. He also received 1991 Meghnad Saha Award instituted by UGC for outstanding research contribution in theoretical science. Professor Ajay Ghatak is a recipient of several awards, which includes Optical Society of America, Esther Hoffman Baylor Award in recognition of his outstanding contribution to optical science and engineering education. He is also a recipient of SPI Educator Award for his unparalleled global contribution to the field of fiber optics research and his tireless dedication to optics education worldwide and throughout the developing world in 2008. So this is the brief introduction from my side, which we have collected from the front page of the Sum of the Books. And I must admit, whenever he writes a new book, as a complimentary copy I received it. So I thank you also for coming here. And now I invite you to deliver 2018 National Science Day lecture of our organization.
Thank you very much, Professor Sinha, for your very kind introduction. And also your very kind invitation to come to this beautiful campus. It is always good to get out of Delhi, come to a very clean place, and it is very rejuvenating. I am indeed extremely happy to be here, meet so many dedicated scientists. And what has most impressed me, in addition to the beauty of your beautiful campus, is the fact that so many technologies are getting developed. From the field of photonics to the field of devices for aircraft technology and the device to read from the blind. These are some of them that I have seen, and I'm really amazed at what all has been achieved during the past few years. So amazed as well as very proud. So with that initial word, I would like to start my Science Day lecture. Half of it will be physics-based, Raman effect, and the remaining half will be on brief history of development of science in India. So I have about 50-55 minutes. At 25 minutes, I must switch off to the other part. You know, exactly 90 years ago, on this very day, on 28th February 1928, read this slide, particularly the younger generation. It was K.S. Krishnan who discovered the Raman effect. He was carrying out experiments of scattering, and he observed what is now known as Raman effect. K.S. Krishnan was a student of C.V. Raman, PhD student, and he made a newspaper announcement on 29th February. Right now it is exactly 3:30 or 31. Raman effect is a scattering process. So many of you are physicists, so you will find it very elementary. But for non-physicists, I'm saying it for completeness, that what is scattering? So let us suppose you have a positively charged alpha particle and this is a positively charged nucleus, so they repel each other. So as it approaches, it gets repelled and it travels in a different direction. This process of a particle coming in and then traveling in a different direction is known as a scattering process. This is also a scattering process in which an object comes near the sun and gets attracted by it and then goes away to another direction. So, for example, this is a real. This is what actually that has happened on July 29, 2017. An object was at this position, and then on September 9, it was in this position, and then it went off. In the former case, in the case of alpha particles, it was a force of repulsion, and in this case, it is a force of attraction. But in both cases, the trajectory is a hyperbola, and in both cases, we have a scattering. That is, a particle coming in, interacting with the force, and then getting scattered in a different direction. So, Rayleigh scattering, which has very important ramifications, in which you have an incident beam, like let us suppose a laser beam coming in, and then interacts with molecules like the present in the air, like nitrogen and oxygen, and the light beam gets scattered in different directions. So this is known as Rayleigh scattering, which is proportional to the fourth power of the wavelength. So higher the wavelength, smaller will be the Rayleigh scattering. And as you all would know, that this is the visible spectrum. The blue region of the visible spectrum has a wavelength of 0.4 micron. 1 micron is a millionth of a meter, and 0.7 micron is the wavelength in the red region. So therefore, the blue component, which has the smaller wavelength, will get scattered more in comparison to the red component. And that is the reason why our sky is blue. Because the light coming in hits the air molecules, nitrogen, oxygen, and all that is there, and the blue component gets scattered predominantly and in comparison to the red component, and so therefore our sky looks blue during the daytime, and our setting sun looks red. And here in this case, it is looking almost yellow, but it looks very reddish because the blue component gets scattered out, and only the red component reaches our eye. So here, this is an optical fiber, and the laser beam is passing through that, and the fiber itself glows, and that is because of the phenomenon of Rayleigh scattering. The light passing through the optical fiber interacts with the silicon dioxide molecules, gets scattered, and that is how we see the light coming out from the fiber. So on the surface of the moon, as you all know, there is no atmosphere, so there is no Rayleigh scattering, and so therefore during the daytime the sky is dark, and the sky is not blue, it is dark, and the setting sun is white in color. Now let me go to another aspect of matter. The simplest atom is the hydrogen atom. Now it consists of, in the simple model of the hydrogen atom, which was put forward by Niels Bohr in 1913, the proton is sitting at the center and the electron rotates in discrete circular orbits. The orbits are such that the angular momentum of the electron, NVR, is an integral multiple of h by 2 pi, where n is equal to 1, 2, 3. In each orbit, that's what he said, that the electron cannot occupy any orbit, it occupies discrete orbit, and the orbits are such that the angular momentum, which is the product of the momentum and the radius, must be an integral multiple of h by 2 pi, where h is a constant known as Planck's constant. It is because of this the atom, the hydrogen atom, exists in discrete states. So therefore, the hydrogen atom can have specific energy levels. So if the hydrogen atom comes from a higher state to a lower state, a radiation is emitted, light is emitted of a particular frequency. So that is how light is emitted. So this is known as the hydrogen atom spectrum. And it consists of discrete lines corresponding to the discrete states of the hydrogen atom. And how do you measure such a spectrum? This is known as a spectrograph, a simple form of a spectrograph. You have a discharge tube with the hydrogen gas, so it glows, it gives you the light. If there is a high voltage discharge, the light is passed through a slit, and then you pass through a prism, and then the prism disperses. The angle of refraction depends on the wavelength. So therefore, the light gets dispersed into different colors. So if you put a photographic plate, you will observe discrete lines. On the other hand, instead of hydrogen, if you have an incandescent light bulb, then it produces a continuous spectrum, like a red hot body, like a very white hot body. Then it will produce a continuous spectrum. Hydrogen atom produces a line spectrum. On the other hand, an incandescent light bulb, which is heated to a very high temperature, produces a continuous spectrum. Now, in the same experiment, if I put the hydrogen gas in between, then the atom, which is at a ground state, will absorb radiation of particular frequency. And so, therefore, on the photographic plate, you will obtain dark lines, because those wavelengths will get absorbed. So, this is known as the absorption spectrum by the hydrogen. So, you have the emission spectrum of hydrogen and the absorption spectrum. So, white light coming in, passing through cool hydrogen gas, then you will have discrete lines, black lines, which will get absorbed by the hydrogen atom in going from the ground state to other higher excited states. So there are two kinds of spectra in spectroscopy. So this band spectrum, as it is called, is a signature of the atom. So if I know the position of the spectral lines, I can predict what type of elements are present. Because each element has its own signature, has its own set of lines, set of discrete lines. It is something which is known as the signature of a particular atom. So therefore, when you see the solar spectrum, light coming from the sun, then you find a large number of dark lines. These were first observed by Fraunhofer, and 45 years after Fraunhofer discovered these lines, Kirchhoff and Bunsen showed that dark lines in the solar spectrum are caused by absorption by chemical elements in the solar atmosphere. So that outside the sun, there is a layer of helium. That is proved only through such experiments, only through such spectroscopy. We know a major part of our universe, the stars and galaxies, because of spectroscopic data. So the field of spectroscopy is one of the greatest, one of great importance and beauty. And you study the positions of the lines, and you can say, you can tell what kind of gases are present on the outer layer of the star. This is for the sun, but for all stars, we have similar spectrum. So this is a molecule. This is the simplest molecule, which is the water molecule, which consists of 2 hydrogen atoms and 1 oxygen atom. Now they, in addition to the electronic states, they also have vibrational energy. There are certain modes of vibration. And what is a mode of vibration? So this is the symmetric stretch vibration, in which the two atoms move at equal distances with a particular frequency. And this frequency, we call it as nu bar. This particular molecule has three modes of vibration. One is this mode, and the other is a slightly antisymmetric stretch, and the third one is a bending. So these correspond to what these give rise to what are known as the vibrational energy states of the molecule. Vibrational energy states of the molecule, and they are also discrete. What I showed in the hydrogen atom were the electronic states, and these are the vibrational states of the molecule. Now, you have molecules in air, and so therefore, if light comes in, the atom is most likely in the ground state. It goes over to a virtual energy state. The photons in the light beam give the energy to the atom to excite it to a higher excited state. And if it comes back to the same state, the scattered radiation has the same wavelength or same frequency. And this is what we know as Rayleigh scattering, which is responsible for the blue sky and the red sun, red setting sun, as I have described earlier. So therefore, light comes in, interacts with the molecule, and gets scattered in different directions. But the wavelength is the same. On the other hand, in the case of Raman scattering, the atom goes up to a vibrational, to a virtual state, and comes back, does not come back to the same state, it comes back to a slightly upper state. So therefore, there is the frequency of this radiation is slightly less, and the wavelength is large. And therefore, I have shown this by a red line. You see, in the previous slide, I have shown both by red lines, saying that the frequency of this with this transition and this transition is the same. There is no change in frequency in Rayleigh scattering. But in Stokes-Raman scattering, it goes up, that I have shown by a green arrow, which has the photon has a greater energy, and then it makes a transition, emitting a slightly lesser energy. And this leads to a spectral line which has a slightly lower frequency and greater, and therefore greater wavelength. On the other hand, if the molecule is in the higher vibrational state, then it can go up and it can come down to emitting a photon of slightly higher energy. But since most molecules are in their ground state, so therefore the probability of the molecule being in the higher state is small, and so therefore anti-Stokes-Raman scattering will be very weak. So therefore, this is the Raman scattering experiment. You pass. This is how Raman did his initial experiment, that he allowed sunlight to pass through a violet filter. So the light that comes out of the violet filter is violet in color. You make it incident on a liquid, and you obtain Rayleigh scattering and Raman scattering. The Rayleigh scattering will correspond to the same frequency, and the Raman scattering will be either displaced to the right or displaced to the left. So this photograph I have taken from the Nobel lecture of C.V. Raman. As I will tell you in a moment, he received the 1930 Nobel Prize, and in his lecture in 1930, he showed this. This is the Raman scattering of bicarbon tetrachloride. So you see, these, let's suppose let us forget about this line. Let us consider this line. So this is the Rayleigh scattered light. That is the incident light. Incident light is 4358 angstroms. That is the wavelength. These are higher wavelength, smaller frequency. So these are the Raman-Stokes lines. And the difference between the frequency of this and this corresponds to the difference of the internal energy states. So by measuring the frequency difference between this line and this line, and this line and this line, I can tell you the vibrational energy states. And by measuring their intensity, I can also tell them the structure, the bending angle and things like that. This particular thing has been taken, this particular spectrum has been taken by Mercury lab. Now, Mercury has two lines, two prominent lines in the 4000 angstrom region. One has a wavelength 4358 angstrom, that is 0.4358 microns. And this is 0.4046 microns. So this is the higher wavelength region, and this is the lower wavelength region. So these are the anti-Stokes lines, and these are the Stokes lines. The important feature that K.S. Krishnan immediately realized that the frequency difference between these two is the same as the frequency difference between these two. So they correspond. So therefore, the Raman shift, this shift is known as the Raman shift. This shift is independent of the incident frequency that Krishnan had observed on February 28, 1928, and that it depends only on the vibrational energy states of the molecule. So it is a signature of the molecule itself. So it's a remarkable tool. And immediately people realize that this can be used in determining the structure and detailed properties of molecules. So overnight, Raman spectra became an extremely important tool for analyzing molecules. And that is the beauty of this spectroscopy. As I told you before, the atomic spectral lines is the only tool to determine all the lines that are present in the universe. Similarly, here, the molecular lines, these lines, the Raman lines, are a signature of the molecule. So by a careful study of these scattered frequencies, their intensities and their spacings, one can find the structure of the molecules. And that is the great importance of the Raman spectrum. So this is a photograph of Raman and his spectrograph, which is now displayed in the Indian Association for Cultivation of Science. And this right-hand side photograph was taken by myself a few weeks back when I visited their institute. And below it is written, the first Raman spectrum was obtained with this spectrograph. And what did this contain? So you have a mercury lamp on the left, and then there is a liquid just below this, just on the left of the spectrograph, and the light falls on a prism, and the dispersed light falls on a photographic. That's it. That is the spectrograph, and this spectrograph costed 150 rupees, which he wanted, and this was donated by the industrialist R.D. Birla, I think. So on 8th March 1928, C.V. Raman communicated a paper entitled A Change of Wavelength in Light Scattering to Nature, one of the most premier journals in the world. And the paper was published on 21st April 1928. And this is the paper. This is a photocopy of the paper that he published in 1928, A Change of Wavelength in Light Scattering. So once again, Rayleigh scattering, there is no change in wavelength, and in Raman scattering, there is a change in the wavelength because of the vibrational motion of the molecule. So therefore, it gives you the vibrational energy levels of the molecule, and by a careful study of that, you can determine the molecular structure. So this is the paper itself. The unfortunate part which many people feel, and there a lot has been written, that although in the first line he does write that further observations by Mr. Krishnan and myself, it was really observations by only Mr. Krishnan, but he signed, but he wrote the paper with just his name. So it came to be known as Raman effect and not Raman Krishnan, which many feel that it should have been Raman Krishnan. And it was from 210 Bobara Street in Canada. I will tell you in a moment. So this is from the diary of K.S. Krishnan. So went to the association only, this is from the diary as quoted in a very authoritative book on C.V. Raman by Venkataraman. So went to the association only in the afternoon. Prof Raman was there, and we proceeded to examine the influence of the wavelength of the incident light on the phenomenon. So it is on that day Krishnan discovered Raman. So for which he got the Nobel Prize and later the Bharat Ratna. And this is his apparatus that C.V. Raman is showing to his guests. So let me briefly tell you about fiber optic communication. You know, today you have cell phones, you can call up Bombay, Delhi, and everywhere with almost no money. The cost of communication has come. It's a revolution that has happened during the last 15 years, 20 years. And that is because of fiber optics. And that fiber optics is light gets through the fiber, and therefore information you send in the form of light pulses, and they are under the Atlantic and under the Pacific, and it has such a huge information carrying capacity, and in which, I mean, many of people working here, Mr. Sena himself, we have been working in the physics of the optical fiber. So the pulse gets attenuated. So the question is, because when they propagate, they get slightly absorbed, slightly less scattered, and the pulse gets, so information, let's suppose I'm speaking of the telephone, then you have a digital signals, that is suppose 64,000 bits per second, and as they propagate to the fiber, it gets attenuated. So we must have optical amplifiers. And the question is, can we have direct amplification of optical pulses? For that, I will tell you the simple principle that if the atom is in a higher excited state, it emits a photon, goes to the lower state, and this is known as the phenomenon of spontaneous emission. On the other hand, if the atom is in the ground state, the radiation of a particular frequency, HU, which is equal to E2, can pump the atom from the ground state to the higher excited state. This is known as stimulated absorption. What Einstein said was that if the atom is in the higher excited state, then the radiation of a particular frequency can stimulate the emission. It stimulates the emission. And what Richard Dorman said, that this process leads to amplification of the beam. So that stimulated emission results in the amplification of the beam. So as the radiation of a particular frequency sees an atom in an excited state, in the process it gets amplified. And this is the acronym laser, light amplification. Light amplification through stimulated emission of radiation. So what Einstein also said, that the probability of stimulated emission is the same as the probability of stimulated absorption. In normal temperature, most atoms will be in the ground state, and so therefore there will be larger number of atoms in the ground state, smaller number of atoms in the excited state. So there will be smaller number of emission, larger number of absorption, resulting in the attenuation of the beam. In 1951, Charles Strong suggested that if somehow I can make the atoms sit on a higher level, large number of atoms, and create what is known as population inversion, then there will be a greater number of stimulated emission, smaller number of stimulated absorption, resulting in the amplification of the beam. And this is once again the acronym LASER, light amplification through stimulated emission of radiation. So what you don't do is that you have a fiber, here thin optical fiber, which I have shown in the previous slide. You dope the core of the fiber with erbium. And erbium has these energy states. So this is the ground state, which is little broad. You pop it with a 980 nanometer laser to a higher state. It immediately, within a microsecond, it de-excites to E2. And there it sits for a very long time. So that is 10 milliseconds, and the above is 1 microsecond. So that is 10,000 times, the half-life is 10,000 times more than the half-life of E3. So most of the erbium atoms are in the ground state. You use a 980 nanometer laser to pump these atoms higher, and then it immediately goes there. And this half-life is very large, so it sits there. So if the pump power is large, then there will be a greater number of atoms in the state E2 than in E1, and you will create a state of population inversion. And why do we choose erbium? Because this energy difference corresponds to a wavelength of about 15 nanometer, which is the wavelength that is used in all optical communication systems. Through when you telephone, through your cell phone, it goes to the nearby tower, and from the tower, the fiber takes over and takes your message to Bombay or London or anywhere. And the revolution that has happened is because of the fact that we are in the optical region, where the frequencies are large, and therefore the information carrying capacity is phenomenally large. So therefore, light from the pump supplies energy to elevate the erbium ions to the excited state. It immediately de-excites, and you have a larger number of atoms in E2. And so therefore, if you have a signal at this wavelength, then that will get amplified through stimulated emission of radiation. So this is my simple device, erbium fiber amplifier looks like. You have a laser, which is a coupler, is inserted to this fiber, and this pump laser creates a population inversion, and you have a signal at 1550, which is the signal carrying your voice, and it gets amplified. And this is one of the revolutions that has happened, the erbium fiber amplifier, and that is now made and manufactured in India. This is a high-tech technology, and it is getting manufactured in India. So this is a erbium fiber amplifier device built by a company owned by one of my former students from IIT. Of course, now he is in United States heading the new photon technologies, Ramdas Pillai. And this is the erbium fiber amplifier. A thing like this is under the ocean. And this is a 25 cents coin, which is of the same size as a 1 rupee or a 2 rupee. So the gain of this amplifier is flat. That is from 1530 nanometer to 1560 nanometer, it is flat and is about 30 dB. 30 dB corresponds to a power amplification of about 1000. So therefore, a typical fiber optic communication system, you have a large number of wavelengths getting multiplexed into a very thin fiber, periodically amplified by the optical amplifier, and then demultiplexed on the other side. And this is the reason, the amplifier is the reason why you can send a large number of channels through the optical fiber, thereby one fiber can carry terabits of information. And that is the reason why the cost has come down from there is a systematic decrease in the cost from 1996 to 2001. And now telephone calls are almost free. If you put this fiber between the mirror and if the top power is large, then the radiation will oscillate back and forth and it will start lasing. And that is the fiber laser, which is again a very high-tech device, and it was used in the Kargil war to win the war. And it works like this: that you see, you have a fight. You see, the enemy was on the top of the hill, and we were at the base. So you use a Bofors gun, and then the enemy will see that. But if you use a fiber laser, and the process is very painful, you blind the person, then it is almost instantaneous. So fiber laser not only is used in cutting steel, but also in defense. It has immense application. And because of its application in defense, no one will give us the technology for that. And we have to build that technology ourselves. So I'll conclude this part, this half part, by mentioning what is Raman amplification in silicon fiber. So this is silicon dioxide molecule, and the vibrational state is about 13.2 terahertz. Terahertz is 10 to the power of 12 hertz. So if you have radiation and then silicon dioxide molecule, so this radiation, say 1550 nanometer, it can, part of the energy can be taken up to raise the silicon dioxide molecule, and through Stokes scattering, you will obtain a frequency which is slightly less, so that you have a radiation, it sees a molecule, silicon dioxide molecule, which is glass, the fiber is made of glass, and this is the vibrational energy level of silicon dioxide. So part of the energy of this light goes to excite the atom, to excite the molecule to that state, and the remaining comes out as a Raman-Stokes line. So similarly, you can use the Raman anti-Stokes line to this. So this is what Raman amplification in an optical fiber. So you have a Raman pump which is 13.2 terahertz away from the signal. You pass it, inject into the fiber, into the hair-thin fiber, in the opposite direction, and through stimulated Raman process, Raman scattering, the signal gets amplified. And now, and therefore, I wanted to say that in 1928, Raman discovered Raman effect, Raman and Krishnan discovered Raman effect, which was to become a mechanism for signal amplification in optical communication over 70 years. So that is the tremendous application of Raman, stimulated Raman scattering. So today we take pride in our knowledge economy. I thought I will spend the next 25 minutes on the history. How did we start? You see, we had the Iron Pillar in Delhi, as most of you have seen, built in the 5th century, which appears to have been protected from rust by the application of a thin coating of manganese dioxide. So the thin film coating technology existed 1500 years back. And then we had mathematicians and astronomers like Aryabhatta, Bhaskaracharya. People say Bhaskaracharya knew calculus. And of course, Aryabhatta knew that the planets rotate on their axis. Then we had Nalanda University, which was founded in the 5th century and was one of the first great universities in recorded history. The university was an architectural and environmental masterpiece. At its peak, it had 10,000 students and attracted scholars from Korea, Japan, China, Persia. And the university was burnt down in the year 1197. So this then came a relatively dark period in the development of mathematics and science in India. So what I was trying to tell you is, before the 12th century, the science and technology, not only in India, but also in the entire region, from China to India to Middle East, was very advanced. The first book on optics was written by a person from Iraq, Al-Hasan, and that was written in 1015. And that is why 3 years back we celebrated the International Year of Light. But after that came the relatively dark period in our country. The development of mathematics and science, and which is a lesson for today, did not take place. Religious fanaticism took over in our country. Schools of learning were converted to madrasas, and even the Hindu gurus also succumbed to the influence of Orthodox Vedantism. This was also the dark period in Europe. It was such a dark period that on 17 February 1600, Bruno was burnt to death by the church because he believed that the earth went around the sun and not the other way around. The church believed that it is the sun which went around the earth. And he said that is not correct, because of which he was taken to the market square and burnt alive. Then came the Renaissance. And then came Galileo, who is often called the father of modern physics. Even he was imprisoned for life, because he also believed that the earth went around the sun. But he had to retract his word. Such was the dominance of church. Such was the superstition over the scientists, that what the church said was the ultimate truth. Then Galileo performed the famous experiment that all objects will take the same amount of time in falling through the certain height. Whether it is a heavy ball or a small marble, they will take the same time. And this is in contrast to the earlier belief that the heavier object will fall fast. But that is not true. So he gave the Galileo's laws, and then came Isaac Newton, who made revolutionary contributions to science that about planetary motion, about theory of light, and many other things. And then came the Industrial Revolution in Europe, which started around 1760 and involved, for example, going from hand production method to machines. This Industrial Revolution, which happened in 18th century, did not take place in India. So we were still in the dark age. However, the Industrial Revolution did not take place in India. The starting of the higher education, the first college in India was the Hindu college in India, was the first institution of higher learning in the modern sense in Asia. It was formally opened on 20th January 1817, exactly 200 years back, with 20 scholars. And one of the founders was Raja Ram Mohan Rai. The pioneering discoveries of Jagadish Chandra Bose in physics and plant physiology, and of Prafulla Chandra Ray in industrial chemistry were made in the laboratories of Presidency College. Hindu College became Presidency College, and now Presidency College is known as Presidency University. And people say for his work on microwaves, Jagadish Chandra Bose should have received the Nobel Prize rather than Marconi. This is a great photograph taken in Calcutta in 1930. In the center is Jagadish Chandra Bose. He was a great teacher. And then this is Satyendranath Bose, who is the discoverer of Bose-Einstein statistics, and then Meghnad Saha. All of them are Nobel Prize winners. Of course, none of them got the Nobel Prize other than C.V. Raman, but they were Nobel Prize. Many people feel that they should have got the Nobel Prize. Then Meghnad Saha set up the oldest academy in India, with which I am slightly associated, the National Academy of Sciences in India in 1929. And then in 1857, 3 universities were set up in Madras, Calcutta, and Bombay, similar to the structure of University of London. This is the Madras University. This is your heritage. Today, we say that we are ahead in knowledge And that is because of the base that was created by the British in the 19th century. Calcutta University and then the Bombay University. And then in 1869, in an article entitled, this we have to read very carefully, on the desirability of a national institution for the cultivation of sciences by the natives of India, the great visionary and philanthropist Dr. Mahendralal Sarkar wrote that the prevailing backwardness of the country was due to backwardness of science. And this is true even today. If we say that 30% of our people are below the poverty line, this prevailing we are still a poor country. And the backwardness of the country today is due to backwardness in the emphasis of science and technology. And then the solution that he wrote, Mahendralal Sarkar, was in the vigorous pursuit of sciences by original research. And on 20th July 1876, he founded the Indian Association for the Cultivation of Science at 210 Bowbazar Street, Calcutta. This was the first R&D institution in India, supported not by the government, but by generous public contributions. He went from home to home, from person to person, asked for donations, and he set up this institute. And this is the new campus of IACS, is near now Jadavpur University, and this is the statue of Mahendralal Sarkar, a great visionary. We require such visionary today. And he held lectures by very eminent people at that time. And in that institute, C.V. Raman arrived in Calcutta in June 1907. He was employed by the accounts office. He worked for the British Raj. And while riding a tram to work, he soon spotted the Indian Association for the Cultivation of Science. And he worked there after office hours. He was newly married, and he worked there after office hours and during weekends, and where he eventually did the Nobel Prize winning work in 1928. So I'll conclude by saying that in the year 1893, Swami Vivekananda and Jamshedji Tata were on board a ship going to Canada. Swamiji asked Tata where he was going and what was the mission. And Jamshedji Tata said, Swamiji, I am going with a mission to bring steel industry to our country. To which Swamiji said, this is very important, it is indeed a beautiful mission. And look at the vision of this monk. However, I would like to suggest that you start an institute, a laboratory to do advanced research in this subject. So that even in 1893, Swami Vivekananda, who did not have any background in science, felt that it is only through scientific research that a country can think of going ahead. You can buy technology, but to remove the poverty, you must have scientific research in the country. And inspired by Swami Vivekananda, Jamshedji Tata created the Indian Institute of Science at Bangalore, donating 30 lakhs of his personal money. And of course, I'm very proud of IIT Delhi, but I have no hesitation in saying that IISc Bangalore is the premier institute, the most premier institute in our country. So we have in the past, because of the base that was created by people like Tata, Swami Vivekananda, Mahendralal Sarkar, C.V. Raman, and the British Raj, which created the three universities. So we have done a lot. We have achieved a lot. In last year, in 2017, as all of you will know, ISRO created a world record by sending 104 satellites in a single rocket. This is a tremendous technological achievement of our country. And all indigenous, because no one will give you the technology for such a rocket. Indigenously built, indigenously designed, and it earned billions of dollars. Then we have a very successful nuclear energy program in India. No one will give us the technology either to make a nuclear reactor or to make a nuclear bomb. We have to build it ourselves. And then we have the green revolution. So in the last Many people say that we have not been able to achieve much, but then when you see the achievements, but then I mentioned three great achievements of the post-independent area. One is the space technology, nuclear technology, and the green, and there are many more like that. But therefore, we have achieved a lot. But then, last year, 10 manual scavengers died in the sewers of Delhi, which is really a shame for all of us. And then we had government who advised all of us. This is a very important thing, and I will tell you why. We are still, the educated people are still fooled by these people. And not only the poor and the uneducated, but the educated. The superstitions have to go. We still have to be educated. So Einstein, who was chosen as the person of the century at the turn of the century by the American Time magazine, said, "My religiosity consists of a humble admiration." He was asked, "Do you believe in God?" And he said, "My religiosity consists of a humble admiration of the infinitely superior spirit that reveals itself in the little that we can comprehend about the knowable world." He wrote that we are like little children in front of a huge library. Someone has written those books, someone has arranged them in order. That is my God. Listen to this carefully. I may be wrong. So he saw this bird, something like that. Someone has designed them. There's so much of science and technology in the making of the eye. Someone has designed them. So God is our creator. You look at the color of this fish. Not in tens, not in hundreds, but in thousands. But then he said, and read this carefully, "But I do not believe in the fear of life, in the fear of death, and in blind faith." So the younger generation has to wake up. We have to wake up. I do not, and read this, I do not believe in a God of theology who rewards the good and punishes the evil. I do not believe in a God of theology who rewards the good and punishes the evil. Why did he say that? He said that because in his lifetime, he saw not 100, not 1,000, but hundreds of thousands of children and old people and women starved to death in the Holocaust. And that is happening even today. So if you do good things, you will be rewarded. That is not correct. So therefore, there are no miracles, no government, no astrology. We live in difficult times when peace and human security are facing new challenges at the individual and global level. Education is the key dimension of the long-term process of building peace, tolerance, justice, and intercultural understanding. The reorientation of education to create a better world is truly urgent. So the most important thing, in my opinion, is education, particularly of women, and in the development of science and technology. And rather than where a mosque will be built or where a mandir will be built, that is of no consequence. I should be more careful. I get into arguments even with my family members, and he says that you have become an atheist. I have not become an atheist. I still believe in the existence of God. But the only religion that you have to follow is to have compassion. As I was telling you in the morning, that we all sitting in this room belong to a very fortunate portion of this society. We have tremendous, we must have compassion. We must always look down and see people who do not have 1/10 of what we have. And that is true. And so in fact, Anna Hazare also said that I do not believe in going to a temple. I believe in having compassion and giving to the poor. So this is what DG of UNESCO said. I conclude by saying what Swami Vivekananda had said. Teach yourself, teach everyone his or her real nature. Call upon the sleeping soul and see how it awakes. Power will come, glory will come, goodness will come, purity will come, and everything that is excellent will come when the sleeping soul is roused to self-conscious activity. Thank you.
Thank you, sir, for the simplified and vivid detailing of Raman effect towards the immense fiber application revolution. Thank you again for a journey through the glory of Indian science to the history. Now, it is the time for SPY quiz winners, which was held yesterday. SPY, Society of Photo-Optical Instrumentation Engineers. It is an international not-for-profit professional society for optics and photonics technology. And the winners are, first position goes to Chandra Bhushan Yadav and Yashpal Goyal. Chandra Bhushan Yadav from B3 and Yashpal Goyal from ISTC. And we request our chief guest to kindly present the prizes to the winner. Chandra Bhushan Yadav and Yashpal Goyal. Second position goes to Rahul Atri, Rupesh Batra, both from ISTC. Rahul Atri, Rupesh Batra. Third position attained by Deepak Singh and Simranjeet Singh. Deepak Singh from ISTC, Simranjeet Singh from B3. Deepak Singh and Simranjeet Singh for the third position. Thank you, sir. Now we request our director, Professor Sinha, to present a memento and a shawl to our chief guest, Professor Ajay Kumar Bhatta, to commemorate the moment. We again request also to honor our chief guest with another memento from on the behalf of Optics Division. धन्यवाद.
I feel deeply honored. My God.
अब कार्यक्रम का अति महत्वपूर्ण और अंतिम चरण हमारा अनुरोध है डॉक्टर अमोद कुमार जी की हमारे वरिष्ठतम अनुभवी वैज्ञानिक हैं कि वे समापन कथन दें और साथ ही धन्यवाद.
Very good afternoon to all of you. I am privileged to say a few words in honor of Professor Ajay Ghatak. Respected Professor Ghatak, Professor M. Saha, Fellow, MASI, and formerly Professor of Physics, IIT Delhi, Professor Sinha, Director, CSIO, distinguished guests, press, media, scientists, administration staff of CSIO, research scholars, students, ladies and gentlemen. We are really grateful to Professor Ghatak for accepting our invitation in spite of his busy schedule and delivering this Science Day, National Science Day lecture. Sir, your talk on Raman effect and brief history of development of science in India that has inspired all of us, and particularly the young scientists who are sitting here in this auditorium. In fact, Raman effect, general theory of relativity, special theory of relativity, these are all always some topics, and we are fascinated towards them. And if we have somebody like Professor Ghatak who can clear some doubts, who can throw some light on these topics, really, it's a great thing for us. And like he has said, that science should be pursued, of course, but it's not only science. There is art in science, in fact. And sometimes art fascinates more. I'll tell you an incident from the life of Sir J.C. Bose, in fact. Once he was going with his father somewhere. And on the way, he saw some fire-like thing in a bush. झाड़ी में ना थोड़ी सी कुछ आग सी महसूस हुई. So when he sat in Bengali, he shone, मतलब he was fascinated with it. He liked it like anything. His father said, he thought that this was Hariki Shondor. कितना अच्छा scene है, आग कितना अच्छा. His father said, no, my son, this is not fire. ये जो है, ये जुनून है, जो रात को चमक रहा है. And what he said, my father, why did you tell me the fact? The whole beauty of the thing is lost. You should not have told. I was enjoying it like. So, I mean, that is another way of looking at the things. Professor Sinha, our director, has patiently guided, advised, and supported us in all our activities, and there is hardly any time when we have not sought his advice. All these events become successful due to his intervention, due to his guidance and support. We are also thankful to the staff, administrative staff of CSIU for all the support they have rendered. Then special thanks to Navneet Aulak and our computer Navneet Anand, both have the same name, except the title, for coordinating this event. We are also thankful to the staff of Director Cell, Mr. S.S. Saini and Mr. Satish and others. Last but not least, I thank all the members of CSI family, the audience. Without you, this would not have been so beautiful what it was. You have all encouraged us, and I hope that in future also you will continue to do the same in making this event so successful. Thank you all. Thanks. Thanks a lot.
Thank you, sir. And you all are invited for tea and the lawns of CSI.